Good morning. It's great to be back here for the second year. I was here last year at O'Reilly AI in London talking a little bit about AWS's work in the machine learning field. Today I want to dive into deep reinforcement learning a little bit, talk a little bit about what this field is and how it emerged, talk about a few example use cases. But I'm also going to talk about some work that we've been doing on the developer experience side at AWS to try and get more software developers using this particular type of machine learning tech. I think that's a really interesting challenge that a lot of us can think about. We probably have ideas for exploiting ML to solve business problems and helping advance the agendas of our organizations, but developing the skills that we need in order to make that idea a reality is actually quite a big challenge, and we've been trying to help our customers overcome that through something that we've created to help developers accelerate their ML skills development. That's what I'm going to talk about at the end of this talk. So what is deep reinforcement learning and how did it emerge? Back in the 1950s, there were two emergent areas of research, systems and computer science research. One was trial and error learning as an engineering principle, and most of the research here was actually about trying to, first of all, quantify the amount of time that would be taken for trial and error learning to be done. And then secondly, trying to reduce that elapsed time for trial and error learning by scoping down the problem space. And then secondly, another area of research in optimal control through dynamic programming. This is breaking up complex nonlinear problems into subproblems and then solving those subproblems recursively, and that can really accelerate the rate at which you can solve a complex systems equation. They were combined in the 80s to give us modern reinforcement learning, and then much more recently, this field of deep reinforcement learning has emerged, where we're using neural networks in conjunction with trial and error techniques to build machine learning models that can help us navigate complex real-world problems. This differs from supervised or unsupervised learning because it's a trial and error-based technique, which those other two areas of machine learning, of course, are not. We're not using trial and error in supervised learning, we're using labeled data sets. And we're not using trial and error in unsupervised learning, we're using algorithms that allow us to establish commonality between data and then build models to predict based on that commonality. Things like k-means clustering or topic modeling would fit into that unsupervised category, of course. In contrast to that, with deep reinforcement learning, we are using an agent to perform actions in an environment, and then we're instrumenting that environment to observe its state and offer rewards back to the agent in return for setting that state in a certain way. So the classic example would be a self-driving vehicle where we want to keep our vehicle, quite obviously, on the road, in the right lane, and not hit any obstacles. Okay, so staying on the road in the right lane would yield a reward, and over time our agent would learn how it needed to respond to the environment in order to achieve that objective, using either computer vision, LiDAR, or other sensors to steer our vehicle and keep it in that position, where it would be yielded a reward by being in the right lane and, of course, not hitting any obstacles in the physical environment. Over time, we can learn how to do that with a deep learning neural network, taking inputs and operating the control system through the outputs within that network. How is this applied today? 3 different examples, and I'd like you to grab these slides. I'm sure they'll be available for download from O'Reilly after the event. There's some citations on the bottom here, and there's some really excellent further reading that you can take a look at to learn more about some of the emergent research around these particular use cases. For recommender systems, we are interested in positioning products or opportunities in front of customers in order to maximize a particular goal. In the case of Amazon, of course, we are interested in putting products in front of customers so that they will make a purchase. In the case of YouTube, which is one of the other examples here, and this is one of the best citations actually, if you take a look at this YouTube video from Chen at Google, you will see a really excellent case study for deep reinforcement learning for recommending YouTube videos for customers, for users of YouTube. And one of the most interesting things here is we're not using simulation techniques. We're observing real users as they use that site over time, and we're building a model which optimizes for a longer-term goal. In this case, it's a longer-term goal of user hold time, so getting users to watch more videos, of course, and then secondly, getting them to interact with that video content through likes and comments. And those are the rewards that we will take out of usage of the system by users. So recommender systems is a really popular use case for this kind of technology. Energy control, And we're not just talking here about simple thermostatic control of the temperature in my apartment, of course. We're talking about thermostatic control, temperature control in much, much more complex systems, like data center environments, for example, where the amount of heat generated over time can be very variable. There can be a very complex airflow environment within the data center facility, which introduces further complexity into the system. By applying DRL techniques here, deep reinforcement learning techniques here, we can optimize control of the temperature, cooling, and airflow pressure within the environment to deliver a more efficient cooling environment for data centers at scale. There's quite a lot of examples of that as well. And once again, we're not using simulation here. We're observing the real environment, and we're learning from the characteristics, the observations that are made in the real environment over time. And then lastly, robotics and automation. This is a use case where we can actually use simulation technology. We can build simulated robot environments. It's really enabled by the whole use case is enabled by low-cost and ubiquitous availability of computer vision technology and low-cost edge inference devices. Typically what we'll be doing here is integrating a low-cost floating point accelerator into our robotics hardware system, using that to interpret RGB video that's coming off a camera in the robotics system, and then using an optimized deep learning model to autonomously operate the robotic system for a particular goal. It might be self-driving, it might be materials handling, it might be welding in a manufacturing plant, all enabled using DRL and often trained in a simulation environment. So what are some of the pitfalls? If you're YouTube or another very large, another site with a very large user population, then you can gather the millions to billions of observations that are required to build an effective trial and error learning system using real data input. Okay, but if you're smaller scale than that, the process of gathering feedback to train can actually be quite lengthy. Second challenge can be simulation to reality variance. So if I'm training a robotics handling system inside a simulated robotics environment, I've got to take into account things like lighting variations that might occur in the real world or other environmental variations that might occur in my manufacturing plant. What if the sun falls onto my production line at part of the day and then does not fall onto my production line at another part of the day? How do I build a computer vision model effectively which can cater for different lighting conditions? It sounds trivial, but believe me, it's actually not trivial. It's actually quite difficult to deal with complexity like that. And then lastly, on reward function engineering, let's just take my self-driving car example here to prove the point. So I get 1 point for staying right in the center of the lane, and half a point if I steer off to the periphery of the lane. So my reward function is going to generate most reward points if my car hits every part of the lane by zigzagging down it. It'll get 1 point for being in the middle and half a point for being on the edge. So if that's my reward function, what is my vehicle going to do if I overtrain and allow it to overfit? Probably going to zigzag down that lane in order to maximize its points generation opportunity. It's probably not what we want our system to do. So you have to be very careful in engineering your reward functions to avoid some of those pitfalls. So what did we do at AWS in order to try to get some more developers to on-ramp into using this technology? We created something called AWS Deep Racer, which is a fully integrated environment for building and training reinforcement learning models for self-driving vehicles. Now, they're very small self-driving vehicles. They're 1/18th scale autonomous radio-controlled cars that have a computer vision system integrated in them and an Intel CPU that enables the deep learning model to run on the car, perform inference, and steer the vehicle around the track. When I say it's fully integrated, we provide a development environment for authoring reward functions, training those within a service we have called Amazon SageMaker, which you might have heard more about over the course of the conference here this week, and then using simulation with another AWS service called AWS RoboMaker to enable us to do simulation-based training, trial and error simulation-based training of that deep learning model in a virtual race environment. It's available now, and everybody here can participate in the final race of the league. There's some credits that you should have found on your seats here today. And of course, you can win fame, you can win glory, and you can win a huge trophy if you participate in our competition at AWS reInvent at the end of this year. Thank you.